Hello everyone, my name is Rasmus Nielsen, and today I'd like to present some of our most recent results on selenium solar cells and our monolithic tandem integration with silicon. The motivation for pursuing a tandem with silicon as a bottom cell is not only that the bandgap of silicon is relatively close to being ideal for the lower bandgap absorber, but the technological maturity and the already established economy of scale for silicon-based PV exceeds that of any other candidate by far. However, the ideal photoabsorber for the top cell should then have a bandgap within the range of 1.6 and 2.0 eV, and as it turns out, the list of potential candidates is actually quite limited. Among the high performance candidates, we have perovskites, but stability and toxicity concerns are still to be addressed. And then we have gallium indium phosphide, which is very expensive to manufacture, and it contains indium, which is a critical material. And then we have a few candidates which, in spite of decades of research, have yet to demonstrate high performance. Now, I have also included selenium down here, and I've given it a small star, as it actually performs quite well considering how little research effort has been put into developing this absorbent material. But why is selenium such an interesting candidate? Well, first of all, it doesn't get more simple than an elemental semiconductor. We just need selenium, which is not considered a critical material. In its crystalline phase, selenium grows in these helical quasi-one-dimensional chains and exhibits the wide bandgap that we're interested in with a very high absorption coefficient in the visible region. Finally, it's super easy to fabricate. There is only one stable phase at standard conditions, and the melting point is very low, making it not only compatible with silicon bottom cells and easy to work with, but potentially also really cheap to fabricate. If we take a closer look at the electronic band structure, the valence band edge is far from being parabolic. Therefore, to assess the effective density of states, we have to compute the carrier densities using Brillouin zone integrals, and from there evaluate the effective DOS. This also complicates the determination of the effective masses, as the masses relevant for transport are no longer equivalent to those derived from the density of states. The trigonal symmetry of the crystal makes the inverse conductivity effective mass a second-rank tensor, and by evaluating the tensor elements based on band curvature and symmetry, we get the following results. We do see the influence of the anisotropic nature of the crystal, but the effective masses are actually not as bad as one might think from just eyeballing the valence band curvature. Finally, it's important to note that the lowest energy transition across the bandgap is not direct, but the lowest direct transition is very close in energy to that of the fundamental bandgap. Therefore, one could call the nature of this bandgap quasi-indirect. Finally, it's a good idea to study the native defect chemistry to make sure that trigonal selenium is not intrinsically limited. Fortunately, when you're working with an elemental semiconductor, the number of point defects you need to calculate is only 2. The self-interstitials have the lowest formation energies, but fortunately, it's electrically benign and neutral across most of the bandgap. Vacancies, on the other hand, have moderate formation energies, so we'd expect low but non-negligible concentrations. And as the vacancies exhibit multiple charge transition states within the energy bandgap, these could potentially be problematic. However, we have yet to explicitly calculate the non-radiative recombination rates. In our lab, we fabricate our selenium solar cells using physical vapor deposition techniques. The selenium thin film is synthesized by thermally evaporating an amorphous layer of selenium onto an ultra-thin layer of tellurium followed by an annealing step at 190 degrees centigrade on a hot plate in air to crystallize the deposited film. The purpose of the tellurium layer is just to improve adhesion and uniformity of the selenium thin film. The carrier selective contacts are deposited using magnetron sputtering, and the final result is a photovoltaic device featuring polycrystalline selenium thin film sandwiched between zinc magnesium oxide and molybdenum oxide, as shown in the cross-sectional SEM on the right. If we study the photovoltaic device performance, we actually achieved a record open circuit voltage close to 1 volt. Now, to properly deconvolute transport losses from other non-idealities, we complemented our current voltage measurements with SunSphere C, revealing an ideality factor of 1.89 and a highly encouraging pseudo-fill factor of more than 80%. This result tells us that the relatively low fill factor is mainly limited by parasitic series resistance. Even though these devices are among the best performing selenium solar cells reported to date, the open circuit voltage deficit is quite significant when comparing to the Shockley-Queisser limit. And the overall efficiency is far from tandem integration with silicon to be viable in terms of performance. Nevertheless, I still believe there's a lot of valuable insights to gain from transferring the fabrication process onto a silicon bottom cell at this point. For instance, the first challenge we encountered when exchanging our glass substrate with a silicon bottom cell was the formation of these large crater-like pinholes in the selenium thin film. Given that the silicon substrate is only a few hundred microns thick and exhibits a much higher thermal conductivity than the 2 mm thick glass substrates, the heat exposure experienced by the amorphous selenium film during the crystallization step will be much more abrupt through the substrate. We therefore had to re-optimize the crystallization step just to get a conformal thin film, which may negatively impact the optoelectronic quality of the selenium absorber. The way in which we mitigated the crater formation was by dosing dry oxygen onto the surface of the absorber for 30 seconds immediately before the thermal annealing process. We are not yet certain why this trick works so efficiently, and therefore also uncertain of the exact origin of the crater-like pinhole phenomena, but this just highlights how poorly understood the crystallization of selenium still is. In the end, we managed to transfer the single-junction device structure onto in-house fabricated TOPCon silicon solar cells with a few modifications to the process flow. Here, I'd like to highlight that both of our ohmic contacts needed to be replaced by a transparent conductive oxide, and in this case, that is ITO, and that the polarity of the top cell has changed. Our single junctions were fabricated in a superstrate configuration, where one would just shine light through the substrate, but of course that's not possible when you're doing it on silicon. The first results showed an encouraging open circuit voltage of almost 1.7 volts, but the carrier collection in the top cell is terrible, and the fill factor is also very low. And to better understand the consequences of these modifications that we needed to introduce in the transfer of our process to silicon, we fabricated bifacial single-junction selenium top cells in parallel with the tandems. Fortunately, all of the issues that we encountered on the tandem were actually reproduced on the single junctions, revealing that as we swap out gold and FTO with ITO, there's a huge problem with charge transport, and we observe a very strong polarity dependence as well. To better understand the origin of the transport issue, we carried out photoemission spectroscopy measurements to construct the energy band diagram. As a result of the very low electron affinity of zinc magnesium oxide, a very large transport barrier is formed at the heterointerface to the transparent conductive oxide. The severity of this barrier is a function of both the work function of the transparent conductor as well as the doping density in zinc magnesium oxide, which is very tricky to get high. Now, given that TiO2 is a workhorse in many other thin film PV devices, we investigated whether or not this contact material would be less sensitive to the work function of the TCO. This is indeed the case, but the conduction band offset with selenium is no longer ideal. Guided by these device simulations, we replaced zinc magnesium oxide with TiO2, and the efficiency increased by an order of magnitude. Now, the open circuit voltage dropped by 300 millieV, but this was expected given that the cliff-like conduction band offset between TiO2 and selenium. Another advantage of using TiO2 is that it is much easier to dope highly N-type, which allowed us to increase the depletion region width in selenium substantially. The consequence is a significant improvement in the carrier collection efficiency, as you can see from the EQE. Returning to the open circuit voltage deficit, it's clearly reflected from the lack of photoluminescence at room temperature that we have a very severe non-radiative recombination problem. At cryogenic temperatures, we do see two peaks emerge, but at lower energies than that of the band gap, and we have yet to figure out what exactly these radiative emission bands are a fingerprint of. We have also carried out time-resolved terahertz spectroscopy to analyze the carrier diffusion length, and at a first glance, it looks as if we have both problems with the carrier lifetime and the mobility. However, If we for a second assume that the effective carrier lifetime is reflected by the rapid initial decay in a transient, the mobility sum is actually quite impressive. By changing the carrier lifetime from nano to picoseconds, we see that the experimental open circuit voltage quantitatively matches simulated values, and by increasing the carrier mobility accordingly, the fill factor and short circuit current started looking more right as well. If you for a second buy the premise that the initial decay in our terahertz transient corresponds to that of the free carriers, and the longer decay corresponds to some form of carrier localization, potentially through defect trapping, then the device simulation actually agrees, both in terms of current voltage and quantum efficiency measurements. Given the very low apparent carrier lifetimes, we have started investigating various defect engineering strategies. The first strategy is to lever the chemical potential of the electrons in our thin film during the crystallization, and thus change the enthalpic cost of formation of defects. So we are trying to grow the crystals outside of equilibrium. The result was amazing control over the surface morphology, as you can see from the cross-sectional SEM, and while the fill factor improved to a new record high 63.7%, the open circuit voltage remained unchanged. Now, another thing we are looking into is whether or not halides could play a detrimental role as killer defects. This is motivated by time of flight SIMS measurements, where we clearly observe both fluorine and chlorine in our absorber. And with that, I'd like to conclude my talk, highlighting just a few of the main points. We have demonstrated the first selenium-silicon tandem solar cell, and from these first iterations, we've set forth the challenges that needs to be addressed on a single junction level for tandem integration to be more efficient and viable. In particular, the crystal growth is shown to be incredibly sensitive to the substrate on which it is grown. We also showed that the free carrier dynamics are more likely to be in the picosecond regime. We are still on our way down the rabbit hole in trying to understand the optoelectronic properties of these intriguing thin films, and as a teaser I can say that we've recently carried out carrier result photo hole measurements with researchers from IBM, which complicated our understanding of these properties even further. Finally, we are developing new defect engineering approaches in which we crystallize our thin film using a scanning laser to lever the enthalpic cost of defect formation through the chemical potential of the electrons in our system. And with that, I'd like to acknowledge our group members and collaborators, as well as our funding agencies.